we did this week, so that's what you are facing, Tailor Approximations, and including one problem, I believe, with where you're supposed to find the accuracy to. Okay. In the meantime, this is what we're concerned about, and they slightly try to broaden the view on a different level, because just to have a kind of bird's eye view on functions and approximations. So just to connect what we have been doing, and we kept calling this what we're doing approximations, but what really is behind it is convergence. Okay. So that's, if you look at this error-bound theorem. Okay, so what we have on both the left-hand side and the right-hand side is sequences of numbers. Both of these are sequences of numbers, not of functions, as long as x is fixed. So x is fixed, then f of x is a number, t and x is a number, k is certainly a number, x is a number, minus a. So all of these are just numbers, and you just do a bit of algebra with them. And then you have two sequences. One sequence, and this is the other sequence. The first sequence we're trying to understand, and we understand it with the help of the other sequence. And what other sequence is, we look closer at it next, we realize that sequence is convergent. That sequence of numbers, once again, and it is convergent to 0. Okay, so the sequence on the right converges to 0 for each given x. Okay, which means that so does the sequence on the left. And that is the meaning of approximation. So not just the meaning of approximation, but rather the meaning of some kind of approximating scheme. Because scheme means that it's not one approximation we care about, but rather we could provide any degree of approximation that we asked of. Okay, so somebody asks us to provide 6 decimals like it was last time, we can do it. Any accuracy can be provided. In what sense? In the sense of convergence. So this thing goes to 0, and that is this is the scheme. So for each f, you can find Tn for n large enough. Well, rather, how should I put it? A better way is to say that for every degree of accuracy, there is an n that the Tailor polynomial, which Tailor polynomial will give you that accuracy. Why? Because the whole thing goes to 0. Okay, so you can make that accuracy as high as you like. Okay, so that is it looks more complex, the idea, than it deserves, because the idea of convergence of functions is not really that complicated, because it matches the idea of convergence of numbers, and that's what I try to show you. That's the definition, but really this picture is a very good illustration of that idea. I have a bunch of functions, as you can see them here. So say f1, f2, f3, and then at the end, that function at the bottom, it is, say, f is equal to 0. So you have a special function at the bottom. It is the limit. And this picture illustrates, it's the simplest example of convergence you can think of, and you can see how the graph's getting closer and closer to the graph of that limited function at the bottom. But really, it's always understood the same way, and that is convergence one point at a time. That's why it's called pointwise convergence. If I pick x over here, then I do not care about anything else on the graph. I can concentrate only on what's happening right above x, and then these are just numbers. So these are numbers. The sequence of sliced points from each of the graph gives you a number. That is a sequence of numbers. An example of how this might converge is very easy. In this, here's how you can have a convergence that is illustrated there, given. So take any function, f of x, y equal f of x, and then how about I divide it by n? So I have f n of x equal to f of x divided by n. Okay, then once again, x is fixed. If we fix x, so define a sequence of functions like this, and then fix x. If you want to see the trend of these functions, you fix x, then you look f of x over n, and what's happening with this? A number. This is just a number, and it is divided by larger and larger value of n. So the whole thing goes where? To 0, right? So doesn't matter where your starting point is, it will eventually go to 0 as n goes to infinity, and that's exactly what you see here. So these are, you can think of this as the original function is f, and then the second one is f over 2, f over 3, f over 4. Where do they go? They all go towards 0. Okay, so that's the simplest, probably one of the simplest examples of convergence of functions is simply divide by a larger number, and then you end up with n. On the other hand, here's another example. How about I take, once again, take any f of x, and then define a sequence f n of x equal to f of x plus 1 over n. Okay, now fix x, and I have f of x plus 1 over n plus 1 over n. Where does it go? F of x plus 1 over n. F of x, right. So once again, f of x is a number. X does not vary. And so we have, once again, a very simple convergence. So any function is a limit of a sequence of functions built this way. So these are very simple examples, but I want to now show you that we have seen examples of this convergence in more complex situations in calculus 1 and 2. And they were kind of important. So the last example certainly from this week is important enough, Tailor Approximations. But let's go back to calculus 1, and here's an example. Look at this picture on the right. Does it look familiar? From calculus 1. So this is some kind of function f of y equal f of x. Okay, and then you see these lines. They're straight lines. We're concentrating on this particular point over here. So what are these lines? Each of these lines, say I take this pink line. It passes through the point. The red point, it also passes through this green point. Okay, all these straight lines pass through the red point. In the meantime, what's happening to the green point? Look at what's happening to the green point. That's the second straight line. So say, let me try to number them. So this is, say, F1, F2, F3, F4. All of them are linear, straight lines. So what do you call these lines? What? No, they're secant lines. The limit is the tangent line, right? So which it does not show, I don't think. It is possible one of these is a tangent line, but these are secant lines because they have two intersections, the red and the green. Okay, and that is how we build the tangent line by plotting tangent lines. But we always thought of these in terms of the slope, and the derivative is the limit of the slope of the secant lines. Okay, but if you can recognize in light of our new definition that this is a convergence of functions. Okay, so secant lines converge to the tangent line, and that is the convergence of functions. Okay, so in that sense, you can also think about it as if it is we are getting better and better linear approximations, right? So if we're trying to approximate our behavior of the function around that red point, then each of these functions is an approximation, but at the limit they're getting better and better. At the limit, the tangent line is the best one. Okay, but generally, I want to point out that once again, if I do this trick as I did last time, like this, I cut this out for a particular value of x over here, and what I have is once again nothing but a sequence of points, 1, 2, 3, and they're going somewhere, and they converge a number of points. We just have to carry this out for every value of x. Okay, here's another example from Calculus 1, also convergence of points, of functions, not numbers anymore. Does this look familiar? Riemann sums. So you start with the blue number, right? Then you do the subdivision of the intervals. So starting with 2 intervals, 3, 4 intervals, 8 intervals, and so on, more and more intervals. Every time, and then you build. Say this appears to be what is the left-hand sum, right? The left-hand sum. So this is my subdivision. This is my subdivision into 2, like this, and then what I plotted here in red is a function. So the blue is our function. Okay, that's fine. But the red one is also gives me a function, a sequence of functions. So if I do it in red, this would be say f1, f2, f3, f4, f5. And as you can see what the pattern is, what is happening to the sequence. You can see how that staircase has shorter and shorter steps, and there even f5 is very close to the original function. So they converge to f. They converge to this function f. Okay, so if the function f is well behaved, that's the idea of the Riemann sum. Why these areas, pink areas, they get getting closer and closer to the area, pink area under the graph of the original function. But another way to look at it is to think about simply convergence of functions as they become more and more complicated. But you can see how the gap closes. So if you want to try to measure the distance between the two functions, the blue one and the red one, the gap's getting smaller and smaller until they virtually disappears. Even number 5, the gap is here very, very, very tiny. Okay, so once again, the two basic constructions of Calculus 1 is the secant tangent lines, is a convergence right here. Okay, so secant lines converge to, these do not converge to the secant line. These converge to the tangent. These converge to the tangent line, but so that's the derivative. But if we talk about the Riemann integral, then the convergence is still here, and it is about convergence to the original function f. Okay, these are the two main examples from Calculus 1, and then we will get more and more examples of all this stuff going on. Okay, so let's see. So that all, this is like I said, a kind of a bird's eye view on preceding ideas in a more advanced way. But now we're gonna concentrate on that one part of it, and that is once again Tailor Approximations. And Tailor the word is slightly misleading, because what's important is that we're talking about polynomial approximations. Polynomial approximations. And so what is it? It is a sequence of polynomials that converge to F. So we have now this idea. So T sub n, and now T does stand for Tailor, but really Tailor refers to the actual way we find it. So we found it. The specific formula for the Tailor polynomial is those derivatives. Remember, divided by factorial. So that's good, but the idea is bigger. It doesn't really have to. It makes sense even if you don't have the formula yet. Okay, so and that's the way we're gonna start over. Is just there's a sequence polynomial of polynomials converging to F, and now let's try to investigate what that means. And there are profound consequences. So this means simply that Tnx converges to Fx for each x in the domain of x of F. Okay, if we want to be specific, then and that is not necessarily. Let me put P here. I don't want to refer to go back to Tailor right now. Let's just say we have a sequence convergent, and then we're not going to study right now that convergence. We will concentrate on this. So this is our interest. Just polynomial sequences. Polynomials. It is a sequence. If F is given, then you end up with a sequence of polynomials. What's so special about the sequence is this is in fact a recursive sequence. That's what we have discovered. Recursive meaning that Pn plus 1 of x is equal to Pn of x plus some extra n plus first term. Cn plus 1, what is it, x minus a n plus 1. Okay? Recursive. So they are not unrelated to each other. These polynomials are not unrelated to each other, but rather they build consecutively by adding one extra term to itself. Okay, you can imagine that the examples that we have seen, convergence, really, what does the next element have to do with the previous one? Maybe nothing. But with polynomial approximations, they do. Once again, just they totally share all the terms except for the last one. So you add an extra term and you have a new polynomial of the next degree. So that certainly makes life much easier. So if this is the case, then you know, like a P and X is C naught plus C1 X minus A. Remember, they're centered at A. C2 X minus A squared plus C n minus 1 X minus A n minus 1. It doesn't fit. Okay, let's just take in. C n minus 1 x minus a n minus 1 plus C n x minus a n. Okay, so that's my nth degree polynomial, nth degree polynomial, and then this, we're talking about recursive sequences. So this is P1, this is P naught, this is P1, this is P2. This is Pn minus 1. Okay, so like I said, it is recursive, so we only add one term at a time. And which means that we really don't care about as much about, we could actually have one sequence, and we could write it like all the way through. And so why stop here? While we have infinitely many terms, right? With the Tailor approximation, we were able to point out what these are. So that is our analysis that we done this week, is how, given an f, how to find these terms, and we can find all of them, not only n up to n, all of them. Keep going. We still know them. We also know Cn plus 1, Cn plus 2, and on and on. Just like, as an example, once again, is if f of x is equal to e to the x, then C1, C0, C1, what is that formula is Cn is equal to 1 over n factorial. Okay, 1 over n factorial for all n. So in other words, it is a sequence. It is a sequence. An infinite sequence. Okay, so we know all the way. We know the problems we solved earlier where we went up to some point, and that's why we spoke of Tailor polynomials, because we only need a certain degree. But theoretically speaking, we have all of them. We have all the degrees for all n, and we have all the approximation with all accuracy that you want, which creates a sequence of what? The sequence of, this is x0, sequence of coefficients of Tailor coefficients. So these are Tailor coefficients. Right here. It's a sequence. Okay, so then we can study that sequence. As you can see, in this particular case, the sequence actually converges to 0. Well, if we care, Cn goes to 0. But we don't really care about that much, because our interest is that over there, what we have at the top, and which means that we wanna create a new sequence, and that is a new sequence will be which is marked over there. It is Pn, the sequence of Pn, and see where that sequence goes. So not each term separately. I don't want to look at each term separately, but rather I would like to look at one term plus add together 2 terms, 3 terms together, 4 terms together, and that it creates a new sequence, and that sequence converges somewhere, and we know where it converges. It actually converges to f, as n goes to infinity. So in that sense, what is f? If we understand this as a sequence, so f of x is in fact the limit of Pn x, n goes to infinity. So then, somewhat informally, we could simply take that list over there at the top and say that it's not just converges, it is equal to f. So C0 plus C1x minus a plus on and on plus C n x minus a nth power on. Okay, so that creates an infinite sum. An infinite sum. Also known as a series. So that's the way we're progressing now from sequences to series. Whether they're made of functions or not, we will start with numerical series, and then we'll go back to functions. But in principle, that's what we're talking about. Given a sequence, we don't want to know its limit anymore. Okay. We want to know what happens if we start adding pieces, the elements of the sequence together. Okay, so as an example, you would start with, say, well, here's one sequence as an is equal to 1. Okay, then the series that I could build is this: 1 plus 1 plus 1 plus 1, and dot dot dot, which means that where does this process and it doesn't end anywhere. It is infinite, right? 1 plus 1 plus 1 plus 1. Okay. On the other hand, if I take, say, an is equal to -1 to the n, it is then it alternates between -1 and 1. So then add 1, subtract 1. Add 1, subtract 1. Where does it end up? No. What?
Isn't it fluctuating?
Yeah, and so what's the conclusion? What? Well, we could try to go back and look at it as like this. This is the sequence that we are looking at. Okay, so the only way to understand infinite series is through infinite sequences. And so if I look at these, how many, 1, 2, 3, 4 numbers, it's enough to understand the idea of what I'm talking about. I have 0, I add 1, I will end up with 1. Then I subtract 1, I have 0, add 1, I have 1. Okay? And I keep going. So it fluctuates. Okay, so what is our conclusion about the limit of this sequence? Doesn't exist. Which means that is why the the series then doesn't exist, or we'll also say it diverges. So the series diverges. Over here we say series diverges to infinity, which is not exactly the same. It just goes to infinity or oscillates, and that's why it diverges. This one is tricky. In fact, well, once we understand this, it is really helpful for us to stay away from trouble. The picture that I brought up some time ago, here it is. Remember this picture? So it meant to illustrate what we just did. So you imagine that you have a bunch of people, and then they start digging holes. Okay, so there are no holes, so there's a sum of zeros. But then they dig holes, and at the same time they take that soil and put it in the pile near the hole. Okay. So then, as you can see, then every 0 turns into 1 minus 1, which is the same thing. It is 0, right? Okay, so then it is the sum of 1 minus 1, 1 minus 1 minus 1. Okay, so it is still a sum of zeros. At the next stage, however, let's somebody comes and says, fill the holes. Okay? So you see what's happening next? Well, there was some confusion because I don't think anybody cares. They're filling a different hole. As you can see, they sort of turned around, and they're using the pile not to the left of the hole, but to the right of the hole. Okay, so they're filling the holes. You see how they're filling the holes? It is still, it seems to be the amount of the soil out and in is still the same. It's 1 and -1, but you can see as when they finish the job, that's what happens. All the holes are filled, and yet there is one pile of soil left out. So they went through this process, ending up with an extra pile. Something from nothing. So how do you explain this? Yeah, but still, it appears to be at every time it's the same soil. So it appears that we started with 0. If either you think of it as algebra or otherwise, as you can see, we started with 0 at the top, and we carried out this algebra very carefully. But then we ended up with, see over here, that's the algebraic trick I took here. 1 -1, I put parentheses around rather than 1 and -1, I do -1 and 1. So as you can see, the parentheses have been shifted. Okay, so as you can see, that is the shift of the person. Instead of digging the hole and then putting a pile to the left of it, he is now to the right, and using that pile to fill this hole. Okay, so that's what I'm talking about, is this. Well, like this. So the starting point was this, like this.
So we're assuming there's an infinite number of people working behind.
That's right. Well, that's the certainly underlying reason why this is troublesome, because we are kind of casual about infinities. which probably after studying some calculus you know that you shouldn't be so casual. Okay, but it still needs to be explained, and we now kind of know how to explain why this algebra is illegitimate. So where is the illegitimate step? Because this is fine. 1 plus this is 0, 0, 0, so there is no trouble here. That's not a mistake to say that the answer is 1. 1 plus infinitely many of zeros, even though there are infinitely many of them, it's not trouble, it is 1. So this is fine, this is fine, this is fine. Well, so the computation is fine, that's what I meant to say. So this is fine. In the beginning it also was fine. As you can see, infinitely many zeros added together is 0, so that's okay. And this is also fine. You know, each 0 has been replaced with 1 minus 1. It is 0. So these are all zeros, right? So there is no trouble. The illegitimate step is in the middle. And not because we came to this conclusion that 0 is equal to 1. That's really not the reason. That's the effect. But the illegitimate step, can you explain why this step is wrong?
It doesn't have plus dot dot dot.
It doesn't. No, probably just. Yeah, it's there. It's still infinite. Yeah, it's still infinite. Anyone? Well, I'll think about what we just talked about a minute ago. Is that this picture especially is revealing that all the infinite sums are computed still in a consecutive manner. So we have to look at this picture and ask ourselves, both pictures as a matter of fact, and ask ourselves in what order we are computing it. In what is the process? And at the top, the process is clear. Whatever is in parentheses is a number being added every time, which means that every time you add 0. Okay, starting with 0, you add 0. Okay, so that is a sequence. If I start adding numbers at the top, I will have 0 plus 0, which is 0. I add another 0, which is still 0. Add another 0, still 0. So that's a recursive process. Is what is overlooked here, or rather, sort of hidden out of the view, that the only way to compute infinite sums is in a consecutive manner, or recursively, if you prefer. So at the top, I keep adding zeros to my sum, and that's why I end up with 0. However, at the bottom, what am I adding? I am adding these. So this is the sequence of events. It is in fact the sequence we just looked at. Look at this sequence of 1 minus 1 plus 1, and that we just established over here that the limit doesn't exist. So even though the limits of that expression at the top exists and equal to 0. Okay, so this is 0. The one below it also exists, and it is equal to 1. So 1 plus 0 plus 0 plus 0 plus 0 is equal to 1. So this is legitimate. But the one in the middle, not only it's not equal to the other two, it simply does not exist. So there's no way to make sense the way we have of this expression other than adding one term at a time as they're written. So 1 plus negative 1, computed. Move on to the next step, add 1, computed. Then add negative 1, computed. And on, expanding it in a consecutive manner. And then this is what in the middle we have is a sequence that, not the sequence of numbers that we see, but the sequence of numbers that are circled. And it will be an oscillating sequence. Oscillating between 0 and 1. 0, 1, 0, 1, 0, 1. That's how it's going to... well, it's actually not the same sequence as no, it is the same sequence, except I'm going to be, so this is 0, then this is 1, this is 0, and this is 1. Okay, so that is really the problem of you cannot freely redistribute or add or remove parentheses to an infinite expression because it changes the way you compute it, and the result might be either different or altogether impossible. So that we end up with here an example of an impossible result. And in what sense? In this sense, there is no the expression in the middle is meaningless. Meaningless in the sense of those divergent sequences that we saw in this class. So if the sequence diverges, it is at the end of it is not a number. There is nothing there. It's not even infinity. It's worse than infinity. It is literally nothing. So if you say something doesn't exist, you are not allowed to do anything with it. You cannot do algebra with it. You cannot compare it with any numbers. You cannot ask whether or not it's equal to or not equal to something else. It does not exist. Okay, so that is the warning, and fortunately we know the way to get around it if we carefully represent our summations as sequences. So which is what I have here. My sequence on the right is represented as a limit of a sequence on the left. Okay, so let's try that. So we set aside polynomials, which is they're kind of complicated, and they're we try to make it as simple as possible. So we'll be dealing with numbers again, no functions for a while. So back to numbers. So AN is a sequence. Okay, then we create a new sequence. It's called the sequence of partial sums. So how? P, we will name them P is equal to A1, P2 is equal to A1 plus A2, P3 is equal to A1 plus A2 plus A3, and so on. Pn is equal to the sum of the first n elements of my sequence. A sequence of partial sums. And then the sum of the series AN is the limit of the sequence of partial sums. Okay, so once again, we're not trying to find the limit of the sequence itself. We don't care. We want to create a sum of elements of that sequence and see where that summation takes us. The only way to figure out how to add infinitely many numbers together is through limits. So we have to form a new sequence and look at the limit of that sequence. Okay, so as you can see, so that's one way to say it, but certainly alternatively you simply say Pn plus 1 is equal to Pn in a recursive manner plus An plus 1. So recursive. The same idea. Just add one at a time. But it is a new sequence, and you have to figure out where it's going. Okay. I don't want to. Well, let me give you an example of what I'm talking about. So two sequences that are familiar are 1 over n and 1 over 2 to the n. Okay, so then this is an. I'm talking about the sequence an. So this we did before. I say 1, 2, 3, 4. 1, 1/2, 1/3, 1/4. Okay, this is 1, 2, 3, 4, 1/2, 1/4, 1/8, 1/16, and on and on. So this is familiar. from before. So remember, we looked at some time ago, mid-semester, we talked about sequences. These are sequences, and then you might ask yourself, where does this go as n goes to infinity? As n goes to infinity, 1 over n goes to 0. Similarly, as n goes to infinity, 1 over 2 to the n also goes to 0. Okay, so that's the familiar stuff. And now we make a step further in a kind of a different direction. So I put the partial sum here. I create a new column, and I add Pn. So what does it mean? I will be starting from, according to my formula, I will be simply adding one term at a time. The term that's to the left is added. So I'll have 1 plus 1/2, which is 3/2. There's 1 plus 1/2 plus 1/3, 1 plus 1/2 plus 1/3 plus 1/4. You can see that things get complicated. But they're only complicated if you are not using a computer, which is, I'm going to do that next. But the question becomes, you continue this process on, and the big question is, what is the limit of the sequence, if you can guess? And we'll try to guess. But we also have the same picture here. Once again, I have my sequence of partial sums. So that's the new. The black is the old, the blue one the new. So I'll have 1/2, 1/2 plus 1/4. 1/2 plus 1/4 plus 1/8, 1/4 plus 1/8, 1/2 plus 1/4 plus 1/8 plus 1/16. Okay, and on. And once again, we're asking our question. The question is to what is the limit? Well, let's not try to guess. Let's just go straight to Excel and carry this out. I want to carry this out. Okay, so let's just go ahead. I'll have my ands here. This will be an, or let's make it capital, and I'll put Pn here. Okay, so I'll start with 1, and I'll go on with equal to the previous element plus 1. Okay, so that will take care of ands. And here I will have an, which is 1 over n. Okay, so equal to 1 divided by this thing. Okay, down. That's my sequence. I take it down not too far. Okay, the pattern, I hope, is clear. Do you see a pattern? Well, what's the limit? These are ands. These are ands. That's the column. Column is ands. And where does an go? Look at the bottom. Start with 1, and then at 0.04. Well, we already know that the limit is 0, so that's what it appears to be. So let's carry out summation. So I'm going to start with, I'll just let it equal to this. Okay, and then the next one, this one is equal to the previous one plus the corresponding value of an. 1.5 as planned. So I have only 4 lines in my 4 rows in my column here, but here I can have as many as I like. Okay. So it goes. I'm adding the numbers. So the second column is the numbers that are being added one at a time. Okay. So they are getting smaller and smaller, which means that they're positive, but getting smaller and smaller, which means that there is a growth, and you can see the growth, right? You can see the growth here. So if I could try to plot it, certainly, but you can try to guess what the answer is. Let's do this. What do you think the answer is? What? Okay, let's try it. we got to 6.
Infinity?
It is, the answer is actually infinity. I could go on, and you see it is growing very slowly, but look at how slow it is. I took 729 steps, and I only reached 7. So really the numbers are getting smaller and smaller to be added, but the theoretical result tells us that the answer is actually infinity. So this sequence goes to infinity very, very slowly. Very slowly. If you look at it, it's already flattening out. It's already flattening out, and yet it remains. It will not flatten out. It will go to infinity in a very slow manner. However, on the other hand, this one does not go to infinity. As you can see, we're adding numbers also small and smaller and smaller, but the sequence goes to 0 so much faster that it does add up to a number that's not infinite. Okay, so give me a minute. So if I have, say, bn here, so I'll put, so it is 1 over 1 equal to 1, not 1 over 1 over 2 to the n, 1 over this, no, 2 to this power, right? 2 to this power. Okay, 2 to this power. Okay, okay, down. Okay, so numbers become small very quickly. Over here, I work out p, and well, you see what's happening. This one doesn't seem to converge. So once again, the original sequence on the left, that is my 1 over 2 to the n. It grows to 0 very quickly, but you can also see once we start add them up, it does not grow. It does not grow, and it does appear to converge to 1, and it does. As I could keep going, and it will look exactly the same. Okay, so we just need to theoretically show that indeed the one on the left diverges, the series diverges, on the right it converges. Okay, so we'll do it next time.